Hello. Okay, so this is a summary video, and I think it's easiest to just write a list of what we're going to talk about because we're going to talk about a lot of things. We're going to talk about in this video all of the standard derivative formulas and rules that typically come up when you first learn derivatives in calculus. Implicit differentiation, logarithmic differentiation, how to use log properties with differentiation. We're going to talk about finding higher derivatives and notation with that for both just your general functions and implicit differentiation. We're going to talk about tangent and normal lines, position, velocity, acceleration. So if you want to review one of these things specifically, you can look in the description of this video for time markers of the topics. Also, if you want more instruction or examples, you can look in the description. This is just a review video, so I'm going to go through things pretty quickly and briskly. And otherwise, just, enjoy this complete review of everything about derivative rules that is under an hour. And if you like this video, I suggest you pair this video with my study series. In my study series, I provide 80 plus practice problems for you to try out in different levels of difficulty. So let's start by talking about formulas, and we'll talk about the formal definition of the derivative, which is this formula. You can pause and review that if you'd like. And then there's also the alternative formula. Again, you can pause and just kind of review this if you want. And where I want to start is just looking at an example where we use one of these to calculate the derivative. So it's very important, like when you take a test, that you make sure you know the directions. So if you're told that you have to use the formula, then you should use the formula. You shouldn't just use the rules. I know just by looking at this is 2x minus 3, that would be the derivative, but I have to back that up now with my formula. Now, I will go the harder route. Personally, I think it would be easier to use the alternative definition, but I will just go ahead and use the harder way just in case people want to see that. So let's go ahead and set this up. Now, one thing I recommend when you do this is that you first restate the definition that you are planning to use when you work through that exercise. It just makes it very clear to your instructor of what your plan was. So even if something goes horribly awry after this point, at least like it was clear that you knew kind of what that formula was. Now, for f of x plus h, I'm going to do that part in green or in pink, and then for the f of x, I'll do that part in green. So, okay, I'm going to go ahead and set these pieces up. So I need to plug in x plus h into this function. So that's going to be x plus h squared minus 3 times x plus h, okay? And then I need to subtract off just the whole function, so f of x. So I subtract off x squared minus 3x, and then we divide all of that by h. Okie dokie. So now it's just a matter of multiplying all this stuff out and collecting your like terms and so on and so forth. So let's go through and do that. So let's see, I get x squared plus 2xh plus h squared minus 3x minus 3h minus x squared plus 3x over h. And now I can see that a bunch of stuff will cancel out. So let's see, my 3x's cancel, my x squareds cancel. And so notice how I'm keeping my limit notation consistent because I haven't evaluated the limit yet, right? I'm just simplifying. So what's left over, I've got this 2xh plus h squared minus 3h divided by h. And notice each one of these terms, they can all be divided by h. So I'm going to go ahead and do that. So this becomes the limit as h approaches 0 of 2x. So 2xh divided by h is 2x, and then h, and then minus 3. So as h goes to 0, I can now take this limit pretty easily. This will equal 2x minus 3. And then you want to do a sanity check, right? So if I compare this to what I know the derivative of this would be, yep, I know that's right, so we're good to go. So sometimes you'll be asked to do things like that, and so make sure that you just adhere to the method that you were told to use. So now I want to start just listing some of the basic rules that come up. So we've got the derivative of a constant, the power rule, and the constant multiple rule. You can pause the video if you need to write these down. And then we've also got the derivative sum rule. So you've got two functions, g of x and h of x, so you just take the derivative of each. We've got the derivative of a natural exponent. Again, I'm trying to get through this, so if you need to pause, go for it. And then I've also got the product rule and the quotient rule. So pause here if you want to review those or write them down. Okay, so now let's take a look at a few examples of these. So in this case, I've got e to the x divided by the square root of x minus 4x squared. So this is going to require that we use a couple of the rules. So we're going to use the quotient rule to kind of guide us here. So to take this derivative, first I take the derivative of the top function. So I take the derivative of e to the x, which is just e to the x, and I multiply that by the bottom function. And then I subtract and I leave the top function alone, and I take the derivative of the bottom function, which would be 1/2 x to the negative 1/2 minus 8x minus 8x. Okay, so there's kind of all the work for the top, and then I divide that by the denominator squared. And so there are all my pieces. And so from here, now it's just really a matter of simplification. So I'm going to, let's see, I'm going to factor out this e to the x because it's in both parts of the numerator, so I'll factor that out. And then I get the square root of x minus 4x squared, let's see, minus 1/2 x to the negative 1/2 plus 8x. So remember, you have to distribute this minus sign in, so notice that I flipped the signs here. And then I'll just divide all of that by the denominator. And you could simplify this farther, but for our purposes of review, we'll say that this is fine for now. Okay, so for b here, so we have to use the product rule. I've got 5x to the pi times e to the x. So this will be my first function, and this will be my second function. So if I want to take the derivative of this, I need to take the derivative of 5x to the pi. So remember, like sometimes people get really thrown off by what to do with this pi. But the thing to keep in mind, what is pi? Pi is just that number, right? It's just a decimal. So you just treat it like a number, that's it. So you still bring the exponent down. So I've got this constant 5 times pi now, x pi minus 1, x to the pi minus 1, that's it. And remember, you multiply that by e to the x. Okay, and now we're still using the product rule, so this will be 5x to the pi. The derivative of e to the x is just e to the x, so there you go, there's your derivative. So next, let's review some trig rules and the chain rule. So here are the derivatives for sine, cosine, and tangent. Again, you can pause the video if you want to write them down. And then here are the other trig rules: cotangent, secant, cosecant. Pause here if you'd like. And finally, we have the chain rule. So for all of these rules, if you need a deeper explanation of them, I have videos of all of that. Again, then we're just kind of reviewing here. So let's look at a few examples. And I thought it would be good to start by looking at an example where we have to use both the chain rule and trig rules. So for a here, so if I take the derivative, so now I've got to use the chain rule. So the first thing that we want to do is just identify the outside and the inside functions for this. So the outermost function will be sine, and the innermost function will be e to the x. So I'll color code my derivatives as I take them. The derivative of sine is cosine, and then remember, you leave the inside function intact, and then you multiply that by the derivative of the inside function, which will just be e to the x. So in the end, my answer will be e to the x cosine of e to the x. Okay, so for g here, so now I've got to use the quotient rule for this. So as I set up my derivative, so first I take the derivative of the top, the derivative of e to the x is just e to the x, and I multiply that by the bottom function, which is just tangent of x. Then I leave the top function alone, e to the x, and I take the derivative of the bottom function, which will be secant squared x, and I can divide all of that by the denominator squared. So there's your function, or your derivative. Okay, so for c here, so now I actually have the chain rule being used multiple times. So just to identify kind of where all my functions are. So sine is the outermost function, then I have e, and then I have 3x plus 1. So let's go ahead and take the derivative. So starting with the outermost function, the derivative of sine is cosine, and I leave all the inside stuff intact. Then the derivative of e is just, well, e to the x is just e to the x. So I'll write e, and I'll leave, again, that whole inside function intact. and then I'll multiply that by the derivative of the innermost function, which will just be 3. So there are all my pieces. So now I just want to write this out nicely. So we'll call this 3x to the 3x plus 1 times cosine of e to the 3x plus 1. Okay, and so for h here, so now we have like the super chain rule. So, all right. So once again, we want to kind of go the same route where notice here I have my outermost function is secant. Then the next one in will be sine. Actually, the next one in is this entire guy here. And then as we're taking the derivative here, we're going to have to apply the chain rule to this. And we'll worry about this when we get there, okay? So let's just start setting this up. So let's see, I've got h prime of x, so I'll color code these. The derivative of secant is secant tangent. Now, this can be a little bit confusing. So let me just like reference this for a moment just to give you a little bit of a visual. So here's my derivative for secant. So remember, it's secant x tangent x. So where I see those x's, I'm just going to replace each of those x's with the whole inside function. So that can be a little disorienting, I guess. So this will be secant, and then I have sine x plus 3x squared plus 5 to the 18th x. And then I also have times tangent, and it's the same thing. Sine x plus 3x squared plus 5 to the 18th. So that is the whole outside function, secant tangent, but with the inside function intact. Then I multiply that by the derivative of the inside function. So the derivative of sine is cosine. And then when I get to this function, now I have to use the chain rule again. So my outermost function in this case is this thing to the 18th, and my innermost function is this 3x squared plus 5. So I will bring the 18 down. I leave the whole inside function intact. I kind of ignore it for now. And then I multiply this by the derivative of the inside function, which is 6x. And there's everything. Whew, it's a lot. So, all right. Then I really don't have like a lot I can do to make this look nicer. So I have secant, I have just this whole crazy long thing. And then secant, tangent, and then, let's see, times, let's see, this will be cosine, oops, I dropped the x, my bad, cosine of x, cosine x, and then plus 108x times 3x squared plus 5 to the 17th. And so there's your derivative. So that one's a little tricky. Next, I'm going to show you all the rules for logarithms, general exponentials, and inverse trig functions. So here are the derivatives for the natural logarithm and the general exponential. Pause if you need to. And also here is just the derivative for a general logarithm. Again, pause if you need to write that down. And now as we go into the inverse trig functions, so just a reminder, so for the inverse sine function, it can be presented as one of two ways. I always write it like this. I think some books write it down like this. So this means inverse trig function, just a reminder. So here is half of the list for our inverse trig functions, the structure of the derivative. Again, you can pause if you need to write those down. Not all classes go through inverse trig derivatives. I teach them. So of course, if your class doesn't do this, then you can just modify this video to your needs. And then here's the other list. Again, you can pause here if you need. Okay, so now what I want to do is I want to just take a couple more derivatives just to kind of refresh how do we use those rules in action. So from here, to take the derivative of this, so I have f prime of x. So the outermost function, we have to use the chain rule again. So the outermost function is this log base 3, and then the innermost function is this x to the 5th. So what I want to think about is this would be technically, so maybe I'll refresh your memory again. So for a general logarithm, so it would normally be 1 over x times the natural log of a. However, in this case, where there's an x, I'm just going to replace it with that inside function. Okay. So this will be 1 over x to the 5th times the natural log of 3, and then I multiply this by the derivative of x to the 5th, so that'll be times 5x to the 4th, and now I can just simplify this. So this will simplify as 5 over x times the natural log of 3. Okay, so for y here, so for b here, so I have the natural log of sine of 4 to the x. So once again, we might want to use the chain rule, and we'll just identify. So the outermost function is the natural log, the next function is sine, and then the innermost function is 4 to the x. So if I take the derivative of this, so the derivative of the natural log of x would be 1 over x. Now in this case, it'll be 1 over all the inside stuff. So this will be 1, oops, let me change my color. Actually, I'll color code here. 1 over sine of 4 to the x, okay? Then we multiply that by the derivative of the next function, i.e. sine. The derivative of sine is cosine, and once again, I leave that inside function intact, all right? And then finally, I multiply this by the derivative of 4 to the x, which will be 4 to the x times the natural log of 4. So there's everything that goes into my derivative. So then, let's see, this will simplify as 4 to the x times the natural log of 4 times cosine of 4 to the x over sine of 4 to the x. All right, so for c here, we've got g of x equals the inverse sine of the square root of x. So we're going to use the chain rule again. So here with inverse sine, so that's our outermost function, and the square root of x is the innermost function. So for this derivative, so just to quickly remind you of what that form is. So we've got 1 over the square root of 1 minus x squared, except where there's that x, we're going to replace it with the inside function, okay? So, all right, so I've got 1 over the square root of 1 minus, and the inside function was the square root of x, so that's squared, okay? And then I multiply that by the derivative of this inside function, so the derivative of the square root of x is 1/2 times x to the negative 1/2. And so then just to simplify this, so this will simplify as 1 over, we'll say 2 times the square root of x times the square root of 1 minus x. That's it, yeah, just 1 minus x. And then what we could do, just to simplify this a little bit farther, we can now multiply the square root of x in. So this will equal 1 over 2 times x minus x squared. And so that would be as far as we can simplify that. Okay, and now for d here, so I've got inverse cosecant of sine. So this is my outermost function, this is my innermost function. Okay, so once again, just reminding you of forms here. So this one's a little kooky looking. So I've got this inverse cosecant. So where you see an x, I'm going to replace that with the inside function. So we're going to replace that inside function twice, okay? So this is going to be negative 1 over the absolute value of sine of x times the square root of sine squared x minus 1. So that is getting to the derivative for this cosecant, this inverse cosecant. And now I'm going to multiply that by the derivative of sine of x, which will just be cosine of x. So if I wanted to just make this look nicer, this would be negative cosine of x over the absolute value of sine times the square root of sine squared x minus 1. Now, one tip I want to give you is to make note cards for all of these rules. If you don't have them memorized, you usually need to memorize them all for a test. These are super, super essential in any calculus class because you use these throughout the rest of the class and usually in your next calculus classes. So now I want to turn to implicit differentiation, and so this is probably easiest reviewed if I just jump straight into the example. So if you have no idea what implicit differentiation is, so it's where you can differentiate where you've got both x's and y's in that expression. I have a whole video where I break down kind of why this works and how to work this all out, so I'm just going to kind of plow through this particular example, but you can always go back and kind of review some of my other videos if you'd like. So I start taking the derivative of this, and so the derivative of x squared is 2x. Then when I get to this piece here, this negative xy, so I think of my x as the first function and my y as the second function. Okay, so the derivative of x is just 1, and then that would be 1 times y, so this will be minus y. And then the derivative of y is 1, so this will just leave me with minus x. However, as we know with implicit differentiation, when you take that derivative with respect to, when you take the derivative of y, you have to also include dy dx, just to kind of note you took the derivative of y with respect to x. Okay, so then when I get to this y squared, it's the same story, right? So this would be 2y, but since I took the derivative of y, I write dy dx, and then the derivative of 4 is just 0. So next, I want to solve for dy dx. So these two terms here that do not have a dy dx, I'll put them on the other side. So let's see, this becomes negative x dy dx plus 2y dy dx. So this will become positive y minus 2x. And then I can factor out my dy dx and divide out this part to get dy dx equals y minus 2x over, we'll write this as 2y minus x. And so there's your derivative. Okay, so for B, so we have one more like this. So if you haven't been, I highly recommend that you pause the video and try all the derivatives on your own. Like I said, it's a really great way to help yourself start studying for a test. Okay, so to take the derivative of this one, so I start with the derivative of x squared is 2x. Now, as I move on to this guy here, I'm going to have to be careful. I have to use the product rule. So I have y and I have sine of x. All right, so taking the derivative of y, that would just leave me with 1 times sine x. So this will be sine x, but since I took that derivative of y, I write dy dx, okay? Then I leave the y alone, and I can take the derivative of sine of x, which is cosine of x. All right, so I'm running out of room here, so I'll put the equal sign here. And so now I have to once again use the product rule here. So here's my first function, here's my second function. So taking the derivative of x is just going to leave me with 1, so that 1 times cosine of 4y. And then I leave the x alone, and now I have to take the derivative of cosine of 4y. So now I also have to use the chain rule with this. So this one's kind of a tricky one. So the outermost function is cosine, so the derivative of cosine is negative sine. I leave the inside function intact, and then I multiply that by the derivative of 4y, which is 4. And since I took the derivative of y, I also have to write dy dx. So that was a little bit of a tricky one. Okay, but the goal here is still the same. We ultimately want to solve for dy dx, so we have some things to simplify. So let's see, I've got 2x plus sine x dy dx plus y cosine of x. This equals cosine of 4y minus 4x sine of 4y dy dx. I'm just barely squeezing it in there. Okay, so now my plan of attack is to basically bring these two things that have the dy dx, those are going on the same side, everything else goes to the other side. So we're going to kind of flip-flop things around here. So let's see, I've got sine of x plus 4x sine of 4y. So I'm going to write this with dy dx. So these were the two things that had the dy dx. So I just went ahead and factored out the dy dx and put those two terms together. Hopefully that makes sense. And then on the other side, so let's see, I brought this term over to this side. This cosine of 4y stays here, cosine of 4y. Then the 2y comes over, so minus 2x. And then also I'm going to subtract off this y cosine of x, minus y cosine of x. And now that I have this part factored out, I can write my final answer. I can just divide by this. So my final answer is dy dx equals cosine of 4y minus 2x minus y cosine of x over sine of x plus 4x sine of 4y. And so there you go. A little bit of work for that one. Okay, so next up we're going to talk about logarithmic differentiation. So when do you use logarithmic differentiation? So you could use it to possibly simplify a really complicated derivative, and sometimes you'll of course be like told that you have to use this, but sometimes you just want to use this because it can simplify something really complicated. Or If there's no other way that you can see to really take the derivative, you might have to use logarithmic differentiation to get yourself there. Now I have a whole video where I have broken down logarithmic differentiation, so I'm just once again going to go straight through the examples, but I will drop a link in the description of how to do logarithmic differentiation if you need a review of that. So starting with A here, so this is like the perfect example of using logarithmic differentiation. This thing would be a nightmare to take the derivative of, right? So I've got x squared, square root of 4x squared minus 2 to the 5th, the cube root of x cubed minus 1. Oh my god, it's just so much. So let's jump into using logarithmic differentiation. So to use this, first you take the natural log of each side. And what that's going to allow me to do, so I'm actually going to rewrite this, since this is all of this to the 5th and then this is the square root. I'm going to rewrite this as 4x squared minus 2 to the 5 halves. And then this, just to make my life easier, I'm going to write this to the 1/3. Okay, so I take the natural log of each side, and the reason that I do that is it allows me to break up like all of this. So I'm going to make my life way easier in breaking this up into pieces, because otherwise you have to use the product rule and the chain rule and the quote. Oh, it's just too much. It's really too much. So, okay. I'm going to go ahead and use all of my properties of logarithms to do this. So this will be the natural log of x squared plus the natural log of 4x squared minus 2 to the 5 halves, and then minus the natural log of x cubed minus 1 to the 1/3. Okay, and so then I can bring all of these exponents out in front. So this is going to be a little bit long, but this will be 2 times the natural log of x plus 5 halves times the natural log of, let's see, 4x squared minus 2 minus 1/3 times the natural log of x cubed minus 1. All right, so this is a bit more manageable. I know I have to use the chain rule here, but at least I just have to use the chain rule versus like this monstrosity of a billion rules, right? So let's clear a little space and continue on with this. All right, so now I'm going to implicitly differentiate. So on this side, this will be 1 over y. And you can write dy dx, or you can write y prime. I'm going to write y prime just to try to see if I can save some space. Now I can take the derivative of this side. So this will be 2 times 1 over x. This will just be 2 over x. This will be 5 halves. And now I've got to use the chain rule here. So this will be 1 over 4x squared minus 2. So times 1 over 4x squared minus 2. And then multiply that by the derivative of the inside. So this will be 8x as the derivative of that. And then this will be 1/3 times, so chain rule again. So this will be times, let's see, times 1 over x cubed minus 1 times 3x squared. Whew. All right, so if I clean all of this up, so I've got 2 over x plus, let's see, this becomes 40x over 2 times 4x squared minus 2 minus, let's see, here it looks like the 3's cancel out, so I'm just left with x squared over x cubed minus 1. Okay, so I know that's like a bit of work, but I think that was a bit more straightforward than the original problem that we were given, and so that's exactly why we want to use logarithmic differentiation. However, we're not done. So the tricky thing with this, so when you're using logarithmic differentiation, so if I go back to the original problem, so this was all in terms of x's, so we have to, one, solve for y prime, but also we don't want to have any y's in our problem, because our original problem was all in terms of x's. So to solve for y prime, so you can see that I would have to multiply by y. So let me just write that out real quick. So y prime equals, I'll write it. Okay, so I just wrote the whole thing out to save you guys time in watching this. So this y here we can't have, so then I want to replace that with the original problem. So finally, now I'm going to have, this will be x squared times the square root of, was that 4x squared minus 2 to the 5th over the cube root of x cubed minus 1, and then all of that times 2 over x plus 40x over 2 times 4x squared minus 2 minus x squared over x cubed minus 1. And so, yeah, that is the answer there. And then for B, so this is kind of that example where you can't necessarily like take the derivative of this. So think about this. We have derivative rules for x to a number or a number to the x, but we don't have anything for like x to the x. And so this is a variable to a variable. That's basically like this same idea here. So we don't have a derivative rule for this, and so that's why we have to use logarithmic differentiation. So let me clear this out. So to do this, then you just take the log of each side, natural log of each side. And what this is going to allow you to do is it just instantly makes the problem something we can approach, because now I can bring those exponents down like so. Oops. And now I can take the derivative of each side. So I'm going to use implicit differentiation here. This one's going to be a little different from the first one that we looked at, so this will be a nice comparison. Okay, so this is going to be the natural log of x. The derivative of that is 1 over x, and I multiply that by the natural log of y, so I'm using the product rule. Then I leave the natural log of x alone, and I multiply that by the derivative of the natural log of y, so this will be 1 over y. However, then I have to write the y prime since I took the derivative of y. Going to the other side, I have to use the product rule, so this will be the natural log of x times y prime plus y over x. So there's kind of all the pieces in my derivative. And so now I once again want to solve for y prime. So I'm going to bring everything that has these y primes together on one side. So these things will come over to this side, and then this I'll send over to the other side. So I'm just going to kind of reorganize my information here. So let me factor out the y prime. So I've got that natural log of x. Let's rewrite this as the natural log of x over y minus the natural log of x. And then that's going to equal y over x minus the natural log of y over x. Okay, so let's make a little space. So my final answer now will be y over x minus the natural log of y over x, and then this will be the natural log of x over y minus the natural log of x. And now you probably don't want to have denominators, like you don't want to have a complex fraction. So then what I'm going to do is I'm going to multiply by xy, because that would be the least common denominator between all the fractions. So when I do that, this will give me, let's see, y squared minus y times the natural log of y. And then in the bottom, this will give me x times the natural log of x minus, let's see, xy times the natural log of x. Okay, and so there is your final answer. And so in this case, you don't have to worry about like replacing the y or anything like that. In this case, this was already defined implicitly, so we expect to have a y in the answer. So that's kind of the difference there. So now I want to compare logarithmic differentiation to logarithms and differentiation. So basically, you can use properties of logarithms to make taking some derivatives easier. And I have a review video on how to use logarithm properties, so you can check that out. I made it specifically for calc students, so it's a very quick review if you're rusty on that. So taking a look at this first example here, so this is like a prime example of when you would just use straight up logarithm properties. So notice that if I'm taking the derivative of this, this is already a natural log. I am allowed to break this up, and I don't want to take the derivative of this as it is. So it's kind of similar to logarithmic differentiation, but we can leverage the fact that we've already got the log right here. So what I want to do first then is I want to just break this up. So this becomes the natural log of x plus the natural log of the square root of x plus 1 minus the natural log of x minus 4, and then I can simplify that one more time. So this becomes, I can bring that 1/2 out, and okay, so there's kind of all my pieces. And so now this I can take the derivative of, and I think that's going to be way more straightforward. because now I just take, this will be the natural log of x is 1 over x, and then I've got 1/2 times 1 over x plus 1, and we're using the chain rule here, so the derivative of x plus 1 is just going to be 1, so I'm not going to write times anything, I can just skip over that. And this will be 1 over x minus 4, and this has the same thing. The derivative of x is just 1, so I can just write this as is. So my final answer then will just be 1 over x plus 1 over 2 times x plus 1 minus 1 over x minus 4. Okay, now for b here, so again, we're using properties of logarithms to kind of help us with this. So in this case, I can shorten how many derivatives I have to take. So notice that this is being subtracted, so I can use the quotient rule for this. So I can rewrite this as log base 4 of x over x cubed. And then this I can simplify farther. So this will become y equals log base 4 of 1 over x squared. And maybe instead of writing this as x squared, actually let me write this as x to the negative 2. I just like that more for when I'm using the chain rule. So now I just have to take this one derivative. So, I mean, it's up to you whether or not you think that's a better thing to have. I think it just makes kind of your last steps of simplifying easier at the very least. So, okay, so now I'm going to use the chain rule here. This is my outermost function. This is my innermost function. So this will become 1 over x to the negative second times the natural log of 4, so there's the derivative of my outer function, times the derivative of my inner function, so that'll be negative 2 times x to the negative third. Okay, so now we do want to simplify this a little bit more. So just playing around with some of my derivatives here, or sorry, my exponents here, so that x to the negative second can come on top. And then that x to the negative third can go to the bottom like this. And then I can simplify one more time. So this becomes negative 2 over x times the natural log of 4, because you can simplify these here. Okay, so now that we've gone through all the derivative rules and kind of working with derivatives, I want to do a quick notation review. So let's talk about notation for first derivatives. So all of these symbols indicate that you are taking a first derivative. And then let's talk about second derivatives. So there's all the notation for taking second derivatives. So if you forgot these are common things to see pop up, so you don't want to forget them on a test and then not be sure what you're being asked to do, right? And then let's also just talk about third derivatives and higher. So third derivatives, you're still using like the 3's or y triple prime or f triple prime. But then after the third derivative, then you switch to this system where you just write the number of that derivative. Notice for this, instead of having now like y quadruple prime or whatever, you just write y, and then you would have this parentheses with a 4 here. So that's how your notation works in that case. So to find derivatives, it's really just you just kind of keep going in a lot of ways. So in this case, I have an example. Find the fourth derivative of f of x equals sine of 3x minus e to the negative 2x plus 7. So let's go ahead and take some derivatives now. So super happy fun time. So for the first derivative, so I need to use the chain rule here. So the derivative of sine is cosine, and I write this by 3x. Actually, yeah, and then I will multiply that by 3. And then the derivative of this guy here, so this will be negative e to the negative 2x, so negative e to the negative 2x times the derivative of negative 2x, which is negative 2, and then this 7 at the end falls out, right, because it's a constant. So this will be, my first derivative is 3 cosine of 3x plus 2e to the negative 2x. Okay, so now on to the second derivative. So you can kind of see that this is just going to kind of keep building on itself. So now I have my outer function is cosine. So this will become negative 3 sine of 3x times the derivative of the inner function, which is 3. And then this will be plus 2e to the negative 2x, and then multiply that by negative 2. So my second derivative will be negative 9 sine of 3x minus 4e to the negative 2x. So now we move on to the f triple prime. So now this becomes negative 9 cosine of 3x times 3 minus 4e to the negative 2x times negative 2. So my third derivative here, this will be negative 27 cosine of 3x plus 8e to the negative 2x. And now let me clear some room for the last derivative. All right, last time. So now I take that fourth derivative. So this will become, this will become positive now. So this will be 27 sine of 3x times 3 plus 8e to the negative 2x times negative 2. So for my fourth derivative, I will get 81 sine 3x minus 16e to the negative 2x. Now, I wanted to take a second to compare taking the second derivative with implicit differentiation, because I think in some ways this is a little bit harder. So just as a refresher, the first thing that you want to do here is just, take the first derivative like you normally would. So I start by, this is going to be 3x squared minus 4y cubed, dy dx equals 0. So I got to solve for dy dx. So let's see, this is going to be negative 4y to the third dy dx equals negative 3x squared. And so then I get dy dx equals 3x squared over 4y cubed. Okay, so I'm going to need a little space to take the second derivative, so let me clear some space. So to take the second derivative, so we really just kind of jump right in there and just start taking the second derivative of this side. So I've got to use the quotient rule here. So I take the derivative of the top function, which will be 6x, and I multiply that by the bottom function, 4y cubed, and then I subtract that. I leave the top function alone, so 3x squared, and then I multiply that by the derivative of the bottom function, which will be 12y squared. However, since I took a derivative with respect, or since I took the derivative of y, I will now write dy dx here. And then I divide all of this by 4y cubed. Now notice with, or 4y cubed, and then I square that. Okay, so notice I did not take any derivatives with the denominator here, so this is where I took the derivative. So that's the only place you're going to put that dy dx. So now I simplify this. And, okay, so this is going to be 24 xy cubed minus 36 x squared y squared dy dx over 16 y to the 6. So the thing about this is that you can't have dy dx in your final answer. So this is why you also need to kind of remember your first derivative. So you take this and then you slide it in place of the dy dx, because it's just kind of odd having like a dy dx in your second derivative. So let me clear some space. So for reference, here's our second derivative. Oops, and let me include that. Okay, so now if I replace that dy dx, this is going to be 24xy cubed minus 36x squared y squared times 3x squared over 4y cubed over 16y to the 6. So now I want to simplify again. So this will be d squared y over dx squared. This will be 24xy cubed minus, so let's see, this will be 36 divided by 4 is 9, and then 9 times 3 is 27, so this will be 27x to the 4th, and it's really all of this over y, and then all of this divided by 16y to the 6th. And so now the last thing that you want to do here, you don't want to have a fraction in this within the whole fraction. So I'll just clear a little space again. And now I'm going to multiply the top and bottom here by y so that I can get rid of this y here. So my final answer will be 24xy to the fourth minus 27x to the fourth over 16y to the seventh. So there's your final answer. Okay, so let's move on now to what are the 4 ways to interpret the derivative at a point. So something that kind of bothers me is a lot of times students just think, oh, the derivative is just this formula. But the important thing about the derivative is that you interpret it for what it really is. So 4 things the derivative at a point represents. So first, it is the slope of the function at that point. We'll call that point x naught. Second, the slope of the tangent line to the, it represents the slope of the tangent line to the curve at x naught. Third, it represents, of course, the derivative. And then fourth, it also represents the instantaneous rate of change at that point in time or at that position or whatever. So I want to go back to the first 2 points. Derivatives and tangents and slopes really go hand in hand, and there are usually pretty good questions you can ask to really test whether you understand this. So I have just a few sampling of questions that I think would be pretty common. But if you are looking for more, I highly recommend that you check out my Study with a Math Professor series and then some of my other videos, because I've gone through this a lot in other videos. So the first question I want to go through is one that I think is pretty standard. So find the equation of the tangent line to f of x equals x squared minus 3x plus 1 at 1, negative 1. Okay, so the second you see tangent line, that really means take a derivative. So if I take the derivative of this function, this is going to be 2x minus 3. And I want to find the tangent line. Now remember, for any line, you want to use the point slope form of the line. And this requires that you have a point and a slope. Well, I've got a point, and I just need to figure out what my m is, and I figure out my m by using the derivative. So I need to figure out what is the slope of the line at x equals 1. So I just have to now evaluate this derivative at 1. So this will become 2 times 1 minus 3, so that'll equal negative 1. So this is my m, okay? So now I can really plug in my point and my slope into this equation. So this will become y plus 1 equals negative 1 times x minus 1. And so then I just want to write this in slope-intercept form. So this will become y plus 1 equals negative 1x plus 1. And so in the end, I get y equals x. So there's my tangent line in this case. Now, I have a couple other questions just kind of related to this to kind of expand on this idea, I guess. So let's say that a function has the derivative 3x squared minus 2x. So the question is, do you have enough information to determine the equation of the tangent line at x equals 2? Okay, so here's the deal. I have x equals 2, so one thing that I could do is I could plug in that 2, right? So I'd get 3 times 2 squared minus 2 times 2. So this becomes 12 minus 4, which equals 8. Now, what does this 8 represent? You always want to remind yourself that this represents a slope, m. And to use that point slope formula, so I have y minus y1 equals m times x minus x1. Okay, so this represents the m in this equation, but I need a point. And so here's the problem. I only have the x part of this. I don't have the y part. And since I don't know what the original function is, I don't have enough information to determine what the y coordinate is, so I cannot find the tangent line. So the answer here is no, we cannot find the tangent line because there is no y coordinate. We have no way of getting to that. So this was kind of a tricky question in some ways. Ideally, what you would want to do is you would want to plug this x equals 2 into the original function, and then you would get your y coordinate, and then you'd be ready to go. But since we can't do that, we're stuck. Now, the next question is, what is the slope of the tangent line at x equals negative 3? Can we determine that? We absolutely can. All we have to do in this case is just plug in that negative 3. So this is f prime of negative 3. This is 3 times negative 3 squared minus 2 times negative 3. So this becomes 3 times 9 plus 6. So that's 27 plus 6. So the slope in this case will be 33. So at negative 3, the slope is 33. Now, the next question is, what is the potential form of the original function? Now, you may or may not have seen this yet. I always like to just touch on this briefly. If I know that this is the derivative, I've taken enough derivatives at this point, can I unravel this? To some extent, yes, I can. So if I have the derivative 3x squared, I can pretty confidently say that that probably came from the function x cubed, right? Because if I take the derivative of this, the derivative of x cubed is 3x squared. And then for negative 2x, well, that probably comes from x squared. Now, there is a problem with this, and as far as you can go with this, would be, what if there was some constant? There's no way for us to figure that out right now, right? So we would just write like a plus c, and this would be like the best potential form of the original function. It would look like this. Okay, so one other extension question of this. If you know that negative 1, 4 is a point on f of x, can you determine the original function? So now this builds off of c. So I had that x cubed plus x squared plus c was my potential function. That was like the form of my potential function. But now I have this point, and I can actually determine the original function if I have a point on that function. So what I could do then is I could plug in that negative 1 like this, and I still have that plus c. And I know that when I put all that information in, this has to equal 4. So now I basically have like just an algebraic expression. So this becomes negative 1, oops, and I forgot to square this, negative 1 plus c equals 4. So what you get then is c equals 4. So now this function, I can replace this c, I can replace it, so let me erase the c, I can replace it with 4. So I have enough information now to determine that function. Now, just one other question kind of related to tangent lines and derivatives. Find the equation of the line that is tangent to 3x squared minus 4x and is parallel to y equals 14x minus 2. Okay, so this is another really standard question on working with derivatives. So we've got the original function, and so the first thing I'm going to want to do is take the derivative of it, of course. So this will be 6x minus 4. And I want to figure out what would my x have to be so that it could be parallel to this. So what is the slope of this line? Because this is my desired slope. The slope of this, the slope here is 14. This is in slope-intercept form. Okay, so I want this derivative to be equal to 14. So what I can do is set my derivative equal to 14. And now check this out. I can figure out what that x coordinate's got to be. So I've got 6x will equal 18. So that means that x equals 3. So now I have the slope, and I need to figure out the point. I know the x part of the point. I need to plug this back into the original function to figure out the y coordinate. Because you always go back to the original function for your xy coordinates when you're figuring out tangent lines. You never use your xy coordinates from your derivatives, okay? So this will be f of 3, so let's figure this out. So this becomes 3 times 9 minus 12. Okay, so if I figure that out, let's see, that's 18 minus 12, so that's 6. So I have the point 3, 6. And so now I've got my slope, I've got my point, so I've got everything I need to figure out the equation of this line. So I can take y minus 6 equals 14 times x minus 3. So this becomes, let's see, 14x minus 42. So my equation of the line will be 14x minus 36. And so there you go. Great question to ask just to really figure out if you understand what the concept of the derivative is. Now, the last thing that I want to just touch on is the fourth point in this list, so that the derivative represents the instantaneous rate of change. So what often comes up with that is talking about position, velocity, and acceleration. So position starts with, like, you have a position function at some given time t, and then velocity is really found by taking the derivative of your position function. And then acceleration is just the derivative of your velocity function, or it is the second derivative of your position function. So just to kind of quickly remind you of kind of a standard example, I guess, that might come up with this topic. So I have at time t, the position of a body moving along the s-axis is s equals t cubed plus 6t squared plus 9t feet. So what is the velocity of the object at t equals 3 seconds? So this is really just getting at, can you find the velocity function, which yes, you can. You just take the derivative of the first derivative of the position function. So that first derivative will be 3t squared plus 12t plus 9. And then if I want to know what's going on at 3 seconds, I just plug in 3. So I have v of 3. This will be, let's see, 3 times 9 plus 36 plus 9. So that equals 72, and that'll be 72 feet a second for your units. Okay, and then when will the velocity, or when will the object reach a velocity of 0? So this is really getting at then two parts of this. I've been filming this video for a while. Sorry about that. So, okay, I have my velocity function. So that was, we already said that was, my v was equal to 3t squared plus 12t plus 9. So I want to figure out when this hits a velocity of 0. So this is all I have to figure out then. So I can factor the 3 out of this, and then I can just go ahead and in this case I can factor this out. So this factors as t plus 3 and t plus 1. So this will be either t equals -3 seconds or t equals -1 second. Well, what the heck? Can you have negative time? You can't. So you might solve a problem like this and then get these nonsense answers. And the interpretation here would be then that in this scenario, this will never actually reach the velocity of 0. So the next question is to find the body's acceleration at time t. So this then is really just relying on the fact that we know that acceleration is the derivative of velocity, or it is the second derivative of position. So just to remind you of the velocity function, here is that velocity function. So now we just need to take the derivative again. So this will be 6t plus 12. And in this case, the question just says find the body's acceleration at some random time t. So this is it. You don't have to do anything else. And then just to finish kind of tying some of the basic terms together. So what is the speed of the object at t equals 3 seconds? So speed is equal to the absolute value of velocity. So if I have my velocity function, so that was 3t squared plus 12t plus 9. So if I go ahead and plug in 3 for this, so I think we already did this. So we got that this was 72 seconds. So the speed is going to be equal to the same thing. It's still just going to be 72 seconds. It's going to be 72 feet a second. So that would be the answer, because the answer was already positive. Now, if this were negative, you would just make it into a positive, because again, speed is the absolute value of velocity. All right, so we're just about done with this video. Like I said, this was definitely a bit of a longer one. And I just want to make sure that I cover my bases here. So different books approach derivatives in different ways. So I have really just focused on derivative rules, but there are other topics that can be related to this. So if you are studying for a test and you're using this to study for a test, don't forget to kind of maybe look over some of these things. I do have some other like videos on these topics, so you are free to check those out. So other things that come up, related rates. I did not cover one of actually I did cover one of those in this video, but you can look up more. Or things like maximums or minimums or graphing. Sometimes that comes up when you learn the derivative rules. I do have a video that goes through all of that, so you can check that out. Optimization. So I have a bunch of videos that show different optimization problems. Sometimes that is related to this. It's not in the class that I'm teaching right now, but sometimes it can be in other books. Newton's method is sometimes covered, and then also linearization. So just kind of a reminder, like this is not exhaustive. You might have other little side topics that were also covered, so don't forget to look those up. And all right, guys. That covers everything in this video. So if you found this helpful, please consider leaving me a like or subscribing to the channel. Also check out my Study with a Math Professor series. Hopefully this was helpful to you. If you leave me a comment, give me some feedback, I always appreciate that. And otherwise, I'll catch you guys next time.